It's a classical mechanics graduate level course, right? So all information about the course you can find. Okay, I'm going to keep in our Blackboard. You know how to get there, right? So I will post there a course policy, right? So you can read it, right? So we're going to have 2 midterm exams. Exam dates are not set. We usually, when we get closer to the right point, we will discuss and make a decision about the exam dates, right? So there will be 2 midterm exam and the final exam. All right. So in this course, we're going to discuss. First of all, we use Goldstein book, right? Classical book, right? And we're not going to discuss Newtonian formalism. We will just skip it completely, right? We will start with Lagrangian formalism immediately, right? We'll start with the Delambert's principle, Hamilton's principle, and so on, right? Then we'll move to, after that, we'll move to the Hamilton's principle, right? Canonical transformations, Hamilton-Jacobi equation, right? Hamilton-Jacobi theory, then central forces, but we will emphasize on scattering to decouple undergraduate level course and graduate. So scattering I did not discuss in undergraduate level course, right? So we will do that. Then coupled oscillations and rigid bodies at the end, right? Okay. As I said, no discussions of the Newtonian formalism, but you know that it exists, right? And actually there are 3 formalisms: Newtonian formalism, Lagrangian formalism, and Hamiltonian formalism. And of course, beneath each of these formalisms, there are foundations. Usually foundation is something which cannot be derived, cannot be proved, right? It's just written usually based on observations, right? And then using we accept them like axioms, right? And then using that foundation, we can build the whole castle of this or that formalism, right? For example, what lies behind Newtonian formalism? 3 Newton's laws plus law of gravity, right? So Newton's, what's the beauty of having Newton's first law in the formalism? It allows us to find inertial reference frames, reference frames, right? Basically, we use that Newton's first law as a tool, or as the tool, to find inertial reference frames. So why do we care so much about those inertial reference frames? What's so special about them? And the reason is that we can use Newton's second law, which is basically an equation of motion, only in inertial reference frames. So that simple form F equals ma or mr double dot, right? It can be used only if you are describing the system from a point of view of an inertial reference frame. Right? You cannot use that in a non-inertial reference frame. You have to do some modifications, some changes, and so on, right? Why? Who knows? God created nature this way, right? And then what's the beauty of having Newton's third law? We can only see that if you start looking at a multi-particle system, right? And if you look at the multi-particle system, Newton's third law allows us to wash out all the internal forces. As a result, if you want to describe a motion of, for example, this ball, right? So in this case, you don't have to care about the fact that it consists of gazillion number of particles inside, and there are internal forces between them. All those internal forces can be washed out using Newton's third law, right? So basically, those 3 laws forms the foundation of Newtonian formalism. Now, Lagrangian formalism. In the Lagrangian formalisms, we can present 2 foundations, alternative foundations. You can either start from the Delambert's principle, which we're going to discuss today, And using the Dalembert's principle, we can get the equation of motion, and we can build the whole castle of Lagrangian formalism. Or it can be also constructed based on the Hamiltonian formalism. That will be next class, idea of the next class. And we will discuss the differences between those two foundations, right? Then, what about Hamiltonian formalism? Of course, we're going to discuss it, but why would people introduce that Hamiltonian formalism? Lagrangian formalism is great. You don't have to deal with forces, right? You have to deal only with energies, kinetic potential energy. It's pleasant to work with them, right? Then Lagrange equations have exactly the same form, so easy to deal with constraints and so on. Why would people develop an alternative approach, Hamiltonian formalism? And the simplest answer is this. In order to use, in the Lagrangian formalism is based on two variables, right? Generalized coordinates and generalized velocities, right? We treat them on the same footings, they're independent and so on, right? So generalized velocities in the Lagrangian formalism. But if you try to apply Lagrangian formalism in quantum mechanics, where we don't work, you cannot apply Lagrangian formalism in quantum mechanics, because in quantum mechanics we don't work with velocities. We work with momenta, right? So that's one of the reasons why Hamiltonian formalism was needed. And that's the major difference between Lagrangian and Hamiltonian formalism. We just take Lagrangian formalism, remove generalized velocities, and place generalized momentum. And as a result, we can get Hamiltonian formalism. And we will get that, of course, at some point. Right. Okay, so now back to the Lagrangian formalism, and let's present the foundation. And again, we will start with Dalembert's principle, right? But before we start presenting Dalembert's principle, we need to discuss virtual displacement, right? And what's the major difference between real and virtual displacement? And also we need to answer the question, what's the logic of introducing this strange idea of a virtual displacement, right? So I will write, let me write virtual displacement first. Right. So first, let's start with real displacement, dr. It's a real displacement. So it's nothing to discuss. It's a real displacements which we observe in our life, right? So system, first it's here, then it can move, or it is moved from this point to that point. Time changes, forces can change, right? Anything can change, all right? Just a normal, real displacement. But virtual displacement, delta r, it's a kind of strange idea, virtual displacement, because when you sort of execute this displacement, only position changes. The rest is held constant. For example, time. Of course, it's impossible, right? Nevertheless, virtual displacement is introduced with this condition, when the time is held constant. So basically, in simple words, it's sort of like if you take a system, right, pour on that liquid nitrogen, right, freezes it, move it, displace it by delta R, and then unfreeze and let it leave, right? Example of virtual displacement. But anyway, okay, probably I should write when time is held constant. Okay, and now, again, it's such a strange idea of virtual displacement, right? Why would people 200 or 300 years ago would why would people wanted to introduce this very bizarre idea, displacing the system when the time is held constant? Okay, so let's discuss that first. And let's start with this. When you travel in your everyday life, right, and using GPS, right, you can pick different routes depending on what you want to get. For example, you can pick the route to get to the final point as fast as possible, so you can try to minimize the travel time, right? So that's your criteria, and you will pick routes to minimize time. Or maybe you want to, for example, minimize the travel distance. Maybe roads can be horrible, right? But your travel distance will be the shortest, right? So according to that criteria, minimizing the travel distance, you can pick the path. Or maybe you want to see the most beautiful roads, right? So you want to see the most picturesque places, right? So that's your criteria, and you can pick the path to satisfy that. System, when it chooses a path, right, travel path between initial and the final point, also moves according a certain criteria, certain ideas, right? So the system, a system, wants to minimize an action integral. So every time it will pick the true path to minimize what is called an action integral. Next class, of course, we will show what action integral is, but you all know that, right? And so now the question: how does a system executes the process of choosing the correct path, the true path, to minimize the action integral? And in this, to describe this process of picking the correct path, the virtual displacement is very important. And that's why it was introduced, right? Okay, so before I start discussing, let's look at a video, right? It's one of the Indiana Jones movies, right? I forgot the name. It's where Indiana has to pass a corridor without killing himself, right? And there are tiles, right? And on each tile, there is a letter. I don't know, A, B, I know E, J, right, whatever. And he has to create sort of a path. He can step only on those tiles which matches the letters in the name of God. For example, Jehovah, right? So first J. So first he has to step on a tile with letter J, then tile with E, then H, right? So then O, then V and A, right? So, and that's the criteria to choose the correct path, right? And if you watch that movie, right, so you will see so how he executed his trip. So he would step, let's say he is on, I don't know, letter E, and then he would start basically exploring virtually, imagining the steps. So for example, if I step on that tile, that's letter B. It's not the correct letter, I will die. So it's wrong way, so no. Right. So then this tile, it's I know, C. No, again, it's wrong. This is wrong, wrong. Or here, H. Yeah, that's the next letter. So that's the correct direction for the next step. He would make that step. So you see, he after completing one step, he freezes time and start like a virtually exploring the sort of space for the next step, like a blind person searching for a safe direction. The same here. And basically, mechanical system does the same. Mechanical system does the same. So it comes to a certain spot and start exploring. But of course, criteria is different. So it wants to minimize the action. So if I move this way, so what about my action integral? Okay, so it's, no, something happens, right? So if I travel this way, it's increasing. No, it doesn't work. I don't like that, right? I want to minimize. So it means that I need to move this way. Okay, it's getting smaller, 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 and search for the correct step, which would minimize action integral. So once it found the correct step, right? So it make that again freezes time, and again it start exploring and looking at the action integral. Is it being minimized or not? Right. And then again, next step, and freezes time and exploring and so on. So that's how it works. And that's why virtual displacement was introduced in order to model, right, the process of choosing the correct path. So y versus, let's say, time, so travel time. And let's say first the system is here at y naught and at the initial moment of time t, right? And so now the system is here at this moment of time, and now it has to make a decision where to go, right? Basically, it needs to move itself to the next moment of time of t plus dt. So now the system starts exploring, right? So if it goes, again, so this is the initial position, why not? So if it goes this way, right, and start looking at the action integral, oh, no, it's not minimizing it, right? So it might go this way, again, virtually exploring. No, still not minimizing them. It's still going down, for example, action integral. So maybe over here, it looks like it's getting to the minimum, right? And then if you move to that point, right, so action starts increasing. So obviously it means that this will be minimum, right? Gives a minimum, minimizing the action integral. And so these displacements, right, so these, it will be virtual displacement y1. This will be a virtual displacement, I don't know, y2. This is virtual displacement y3, right? So basically, this virtual displacement leads you from sort of one sort of lifeline to another possible alternative lifeline over system, right? Okay, and so in order to model this process of choosing the correct path, virtual displacement was needed. So it wasn't completely crazy and cuckoo, right, to introduce this virtual displacement. Right. Okay, so now there is another episode again, but now it's from the Back to the Future. That's the second episode, where also it is basically shown. Right, I hope commercials are not going to pop up. Indiana Jones, where is it? Okay, I need to probably increase the screen. Yeah, Back to the Future. Let me increase it to the whole screen and, okay.
Obviously, the time continuum has been disrupted, creating this new temporal event sequence resulting in this alternate reality.
English, Doc.
Let me illustrate. Imagine that this line represents time. Here's the present, 1985.
Sort of like a lifeline.
Past. Prior to this point in time, somewhere in the past, the timeline skewed into this tangent, creating an alternate 1985. Alternate to you, me, and Einstein, but reality for everyone else.
Okay, so it's exactly the same idea, right? So, and the virtual displacement would lead people from one lifeline to the other one, from this reality to that reality, right? So something happened at that particular moment of time, some conditions change, and now a different lifeline is going to minimize or satisfies a given criteria which has to be satisfied, right? So now I can add a different diagram. So let's say this is again y versus t, and it's like in the movie, two lifelines, right, explaining two different realities possible, right, if conditions are changing. And let me draw something like this. So let's say first and the second, and there are two different lifelines. Let's say the first one and the second one, right? So now, what does real displacement do with the system? Real displacement moves the system. Let's say originally the system was here, right? And the real displacement moves the system along a certain lifeline. So, for example, from here it will leave to there, and this will be real displacement, dy. But the virtual displacement, so basically it keeps the system on the same line, on the same function. But the virtual displacement, it's like here, you see different realities, different options, and the virtual displacement allows us to jump between them. And here the same, so virtual displacement will lead us from this line to that line. And on that episode, right, so the virtual displacement would lead them between the realities, between those lifelines. So, and the virtual displacement would be this delta y. Right. Maybe I will also write, so the second episode, which we used Back to the Future. Okay, and this virtual displacement happens to be very, very useful, again, because we basically try to model what happens in nature. And in order to explain behavior of the system, in the process of picking the true path, this virtual displacement was really needed. So it's not completely crazy to introduce, it wasn't completely crazy to introduce virtual displacement back then, right? All right. Again, as I said, it's sort of like a system search, like a blind person searching for the correct path, right? So now, after this, now let's start introducing the foundation. And first, we will introduce a Dalembert's principle, which is basically a foundation behind Lagrangian and Hamiltonian formalism. So now I can put, it's a section 1.4, no, 4. 1.4, so let's first introduce the LE, yeah, Dalembert's principle. And then, of course, we will naturally introduce Lagrange equation, derive Lagrange equation. All right, so let's assume that we have a multi-particle system, completely arbitrary, right? So let's assume that we have n particles. And another thing I want to mention at the very beginning, when I was reviewing foundation behind Newtonian formalism, I should have mentioned also that all those Newton's laws, Newton's second law especially, right, Newton's third law, they were all written for point particles, right? So you cannot apply them directly to, for example, rigid body. No, you need to apply some logic, you need to do some calculations, right, and using Newton's second law for point mass, and then extend those results for a multi-particle system or for a rigid object. All those fundamental laws usually written for point objects, right, for the simplest possible mechanical systems. So n particles, right? So let's say that we have a few of them. Let me draw a few of them. And let's say that this is my reference frame. Right, so I'm describing this system using that reference frame. And let's say this is particle I, right? And let me just write down Newton's second law for that. So what I'm doing, I want to emphasize, it's not a derivation of Dalembert's principle. As I said before, Dalembert's principle cannot be derived. Any principle cannot be derived. Just basically what I'm doing right now is just from educational point of view, it's good to move from something which we know, to a new stuff. And that's what I did in the previous semester in undergraduate level course, first time to introduce Lagrange equations. It was very finicky, very weird. We just basically moved from Newton's second law to Lagrange equations. But again, it's just from educational point of view. Right? All these formulations, foundations, they can stand independently, separately. They don't need support. For example, Lagrangian formalism doesn't need any support from Newtonian formalism. It's a completely independent formalism, equally powerful. There's no single problem, of course, classical problem, which cannot be solved using either Newtonian or Lagrangian formalism. Right? Okay, so what I'm doing right now, it's again another weird educational way of getting the foundation from something which we know. But it's not a derivation. Don't take it as a derivation. Right? So let's write Newton's second law for this particular particle. Right? So of course, all forces acting on that particle equals to the rate of change of its linear momentum. If I use Newton's second law, it means immediately that we're using inertial reference frame. If it wasn't an inertial reference frame, it would be illegal to write this down. Right? Again, that's the connection between Newton's first law and Newton's second law. Right, so this is, I will emphasize, inertial RF, reference frame, not radio frequency, reference frame. Right, so now we can write this. And now let me write this down. Write down this force. Of course, some forces can be forces of constraints, and some are actual forces. So let's split them up. Let's say actual force is Fia, that's the actual force, and plus force of constraints acting on the particle. So let me emphasize. So this is force of constraints. Oops. And these actual forces, I think I called the actual or applied. All right. Okay, so now let's plug them in. And probably first I will write, forces, and also I will move P dot to that side. So it will be, of course, F sub I A plus F small I minus Pi dot. And that's, of course, it must be equal to 0. But I want, of course, we can write this for each of these particles, and there are n of them. So let's add all those equations up. So let's just sum over the whole system. So I can put summation over I from 1 to n. And also, I'm going to take a dot product of this bracket with the virtual displacement, delta Ri. So first I can write this Newton's second law for each particle. Then, of course, I can dot it with virtual displacement. Then I can sum up over the whole system. And every time it will be still equal to 0, because each of those equations are equal to 0. If you multiply this minus that by virtual displacement, it's still 0. Right? And if you add all equations, and each of these equations on the right-hand side has 0, of course, you will still end up with 0. So it must be equal to 0. Right. Okay, so now we can say two statements, for example. First, if you take a dot product, basically work, this is work, right? Work done by the forces of constraints, or in this case, it's actually virtual work. Every time, it's 0. Or we can say, we usually discuss that in undergraduate level course using examples. Or we can say we can restrict ourselves to the systems, where net virtual work done by the forces of constraints is 0. Either way works. We can, after making that statement, this times that will be 0, dotted with that will be 0, and we can, okay, let me first write it down. I will probably write this. Since forces of constraint, the forces of constraints do no work so then basically we can write that summation of Fi, it's difficult to write here at the end because I have a flat surface supporting the whiteboard. It's dotted with delta Ri equals to 0. So since this is true, or we can say let's restrict ourselves to systems where this is true, and what will be left behind, that's what is called the Delambert's principle. So now I can rewrite that and call it Delambert's principle. So summation over the whole system from 1 to n Fi a minus rate of change of the linear momentum dotted with delta R virtual displacement equals to 0. That's what is called a Delambert's principle. Okay, we can frame it. Again, it's don't look at this as a derivation. Again, it's sort of educational point of view, useful transition maybe from Newton's second law to this formalism. I mean, to the foundation of this formalism. Right, so that's what is Delambert's principle. Right. So let me check if I mention everything. Yeah. So basically, yeah, using this Delambert's principle, we will show after this, we will show how to get the equation of motion. All right. Yeah, I was just trying to recall. So from this Delambert's principle, we can get equation of motion, and of course we should be able to predict, get a trajectory, right? And what I want to emphasize on. So what we have here. So this is instantaneous, basically describe instantaneous state of the system, and then in collaboration with the displacement, virtual displacement, using that we can get an equation of motion. It basically means we should be able to describe the system completely using what? Using instantaneous state of the system and a small displacement. So basically this is what is called a differential principle. Next class, when we will introduce Hamilton's principle, in the Hamilton's principle, the idea is kind of, I want to say completely different. Because in the Hamilton's principle, in order to describe the system, in order to get the equation of motion, we will have to consider the whole trip of the system. So we will have to look or somehow analyze the system from the very beginning till the very end in order to get the correct trajectory, in order to get the equation of motion. So Hamilton's principle is an integral principle. This Delambert's principle is differential. So we're getting the equation of motion from basically instantaneous state of the system, but in the Hamilton's principle, we're getting equation of motion from the whole lifespan of the system, right? So differential principle and the Hamilton's principle will be integral. So that's the major differences between Dalembert's and Hamilton's. Although they're both equally powerful, you can, as I said, you can build the whole Lagrangian formalism using Dalembert's principle, or you can build the whole Lagrangian formalism using Hamilton's principle. Right? Just two ways of stating the foundation. Good to have an option, right? Okay, I will probably emphasize that this is a differential principle. Differential principle. Okay, my whiteboard started wobbling a little bit. I need to fix it. Differential principle. Okay, so, and now, yeah, from here we should be able to get an equation of motion. Right? So now let's do that. And let's start with the first. What, or maybe I will put just a small bullet. So first situation. What if a system doesn't have any constraints? Maybe I will write something. If a system does not have constraints, constraints. So basically it means that there are no rods connecting particles or cables, right, or surfaces, no forces of constraints. In that case, if no constraints, what can you say about all these position vectors? R, basically, it's a position vector defining position of each of those particles, right, in the system. If no constraints, all those position vectors are linearly independent. And of course, the virtual displacements also are going to be linearly independent. Ri and delta Ri are linearly independent. And so if they are linearly independent in this sum, it means that these can be correct and can be equal to 0 when each of these factors in the sum is 0. Each of these factors is 0, right? Makes sense, right? So independent, then Fi A minus P dot equals to 0. And of course, we're getting just Newton's second law. Again, you can say what is a strange thing. You started with Newton's second law, moved to this, and again, now you're getting Newton's second law. Again, don't look at this as a derivation. Again, it's just a transition from this to get at least somehow Delambert's principle useful from the educational point of view. But we could have just started from this, because again, it's a principle. It cannot be it cannot be derived. We can just state it as an axiom and start from here, right? Okay, so if system has no constraints, then immediately we're getting Newton's second law, which is an equation of motion, which can be used to describe motion of the system. But, so of course we will get Newton's second law. Okay, awesome. Now, what if a system has constraints? And now we're running into a problem, of course. So let me check if I mentioned everything. Yeah. If a system has constraints, right? Okay, so now if there are constraints, of course, immediately number of degrees of freedom is going down. Number of linearly independent coordinates is going down. So basically now we can say that Ri and delta Ri's are no longer linearly independent. And in that case, we cannot say that these factors in front of those virtual displacements must be 0. No way. That can be, we can say that only if those guys are linearly independent, right? You remember, it's a linear algebra, basically stuff, right? Has constraints, all right? Then delta Ri are linearly dependent, right? And as a result, we cannot say that Fi, you know what? I'm going to drop that upper script, right? No, it's getting annoying, right? So let me forget about that upper script, right? All the forces are going to be actual forces over there, right? So minus Pi dot is no longer 0, and I will put a big sad face. So now we cannot get an equation of motion as easily as in the first case. So what can be done? First of all, of course, we need to reduce number of coordinates, right, to a new set of linearly independent coordinates. And of course, that new set we're going to call as a generalized coordinates, right? Generalized coordinates. So now we're introducing that very important idea of a generalized coordinates, right? So we need to move from Ri, right, to, okay, let me emphasize, so they are linearly dependent to a new set of Qj's. These are linearly independent coordinates. And that new set of linearly independent coordinates, of course, we call generalized coordinates. These are generalized coordinates. Generalized coordinates. Right? And of course, whenever you make a transition from Cartesian to generalized coordinates, you need to show the transformation equation. Transformation equations. Right? So, transformation equations. So let's say, let me write it this way. So Ri, it's a function of Q1 all the way to Qn and possible time dependence. So here, let me show that J spans from 1 to n small. Here I runs from 1 to n capital because I, it's basically counts particles in the system. Let me emphasize on that. So I goes from 1 all the way to n capital, but J to n small. Right? So now, what do we have to do? Basically, now we have to rewrite Dalembert's principle in terms of these generalized coordinates. It means that over here, instead of delta r, we need to get delta q's, right? And of course, summation over here, outside summation, must be over j. So we need to turn that Dalembert's principle inside out, or maybe not inside out, but change. We need to change coordinates, right? Because right now, the way it's written, it doesn't work for us. We need to do something. We need to rewrite it so that we can, if we manage to rewrite in that form, then delta q's will be linearly independent, and of course all those factors in front of those delta q's, we can say, yeah, those factors must be 0, right? So, okay, so now let's rewrite it, but before I start rewriting, let's prepare 2 ingredients, which we will use later when we need them, right? In the process of rewriting that Dalembert's principle. So, a couple of things. So let's start with, okay, let me write 2 ingredients. And then, of course, we will use in the process of transformation. So first, let me write velocity in Cartesian coordinates. It's just basically dr over dt, dri over dt, dri over dt. For now, just for no reason, I want to prepare these 2 ingredients, but of course later on we will use them whenever it's needed. All right, so I want to write it in terms of Q, right? So basically, time dependence can be in this Q1, Q2, Q3, all the way, and also possible time dependence. So I just need to differentiate it properly, right? So there will be summation. Which subscript I use? I think J. No, K. K, of course, from 1 to n small. So it will be partial derivative of Ri with respect to Qk and Qk dot. So that's what we get from this. And then since explicit time dependence is possible, so I can write that partial derivative of Ri with respect to t. So now let's differentiate this with respect to generalized velocity. Generalized velocity is just a q dot. So now d partial derivative, okay, I don't like these steps. So dvi over dqj. Basically velocity over velocity. Velocity in Cartesian coordinates and generalized velocity. All right? Okay, then we also need to remember that Ri is not a function of generalized velocities. I cannot even imagine that. So, as a result, if you differentiate this with respect to Qj, these factors are not going to give us anything. Then dq dot k over, okay, differentiation of qk dot with respect to qj, of course, give us a symbol Kronecker, delta ik, jk, which is going to kill all this sum. Only one term will survive from this sum when k equals to j. Right? So let me write that down. So it will be partial derivative of Ri with respect to qj. Right. And also, if you try to differentiate this Ri with respect to q dot, there's no dependence. This is going to give us 0. So we're getting this equation, which we're going to use today, and I think once or twice in the future. I will tell you. You remember in the first lecture in that we derived that ingredient. So let me frame it with the blue. Right. And it's not that easy, difficult to remember, because basically you're taking, it shows the relationship between, or it shows that the relationship between Cartesian velocity with respect to generalized velocity is the same as the relationship between Cartesian coordinates and generalized coordinate. So VV, RR, basically, right? So it's easy to remember. Right, so that's the first ingredient. Now the second, let's just look at the variation of R. Right, again, in terms of Q. And after that, we should be able to start making a transition. Right, so, and again, it will be all, it all comes from this transformation equation, relating these coordinates. So now, so this is the first ingredient, this is the second ingredient. So variation of Ri, delta Ri. Very simple. Again, we need to vary all of that. So it will be summation. Now I will use J from 1 to n, partial derivative of Ri with respect to Qj, right? And then variation of each of those Qs. So delta Qj. Then, of course, we still have this possible explicit time dependence. Why I'm not writing anything over there related to that time? Because you remember, it's a virtual displacement. Virtual displacement when time is held constant. So variation over time gives us 0, right? Remember, right? Since delta t is going to give us 0. Okay, so that's the second ingredient. Let me also frame it quickly. although with this ingredient we're going to use only today, but this somewhere in the future, remember? Vaguely remember. All right, so now I can invade this part of the whiteboard. Okay, I have Dalembert's principle over there, so I can erase this whole thing. Yeah. I feel sorry for my neighbors. Every morning they have to listen to lectures of physics and hear the noises on my whiteboard. So let's start making a transition step by step. First, let's look at this F dot delta R. Let's make that transition, and then we will, second step, P dot delta R. Right, so let's start. So it will be summation, of course, over I from 1 to n, F I. And again, you remember, we agreed that upper script A, actual applied force, we're going to drop. All those forces will be actual. So dot delta R I, right? Okay, so this prepared ingredient we can use immediately in this equation. And again, you remember how we need to arrange. Okay, let me first write, and then I will start arranging, of course. Summation over I1 to n, Fi dotted with all that mass. Summation over j from 1 to n small, and dri over dqj and delta qj. Right. Again, you remember now the structure which we want to get. We want delta q outside, and of course summation over j must be outside. So let's take the summation over j outside and delta qi outside. So summation over j from 1 to n small, and the rest, of course, I will collect in this bracket. So it will be summation over I to n capital. So then Fi dotted with this derivative, right? Partial derivative of Ri with respect to Qj and delta Qj. Again, I emphasize that that's the format we wanted to have. Delta Q outside, because it's a linearly independent. So we want to have that and summation over j. So now we've created this construction. Let's call it basically what we have. Force dotted with the partial derivative of Cartesian coordinates with respect to generalized coordinates. Let's call this construction as the generalized force. Force is involved with some additional parts, so let's just call it generalized force. All right, so introduce Q, and so summation over I, so J stays outside. So it's a Qj. Okay, I will put 3 lines by definition. By definition. And this is summation over the whole system over all n particles. All right, so summation over I from 1 to n, Fi dotted with that partial derivative. And we call it generalized force. So yeah, we're going to use this expression from time to time in the future. This must be framed in red because it's an important. Those just ingredients, just mathematical, for mathematical simplification in the future. But this is an important quantity, generalized force. Right, and so now we can, of course, rewrite this part of the Dalembert's principle. So it will be again summation over j, qj, delta qj. Right. Q, generalized force, doesn't have to have units of force. The same, this Q, generalized coordinates, doesn't have to have units of length. But the product of these whatever units times these whatever units must give you units of work, energy. Because basically here we have works, right? But again, units of Q, who knows? It depends on the problem. Units of Q, again, who knows? It depends on which generalized coordinates you pick. It can be angle, it can be displacement, it can be anything, right? But the product must give you units of work. Right, so done with this part. Now the second. Let me check if I mentioned everything before I go into the second part. Yeah. Now it's time for to handle that P dot. Right. Maybe I should emphasize. So this is the first term. Now the second term in that Delambert's principle. So summation over I, P I dot and dotted with delta Ri. Right. So second term, of course, Pi we can write explicitly because all those P's is just a linear momentum of point masses. And of course, we know the definition of linear momentum of the point mass, so we don't have to invent here anything crazy. All right, so Mi, probably immediately I will write with V or, yeah, let me skip MV. I will write in terms of MRI double dot, right? Because here it's a P dot, so it will be MRI double dot. Right, and dotted with delta Ri, and again we can recycle the same ingredient. So now I can write that down without thinking. Summation, okay, so this is over I, here summation over J. Partial derivative of Ri with respect to Qj and delta Qj. Basically, we're moving towards Lagrange equation. We're sweating, right, to get, again, that's the foundation, axiom. And now, of course, we need to get an equation which will allow us to get trajectory, life of any system, any mechanical system. So we're basically moving towards Lagrange equation. Again, so now let's rewrite in the form which we want. Q, delta Q outside, summation over J outside, and then we will deal with what will be inside. So summation over J from 1 to n, and let me just write the, let me just immediately, I goes inside, summation over I, Mi, delta Q will be there, so it's a Ri double dot, dotted with delta Ri over delta Qj, right, it's a J, and delta Q outside. Okay. That's the format we want, and now we just need to extract something useful, interesting out of these brackets, out of these parentheses, right? Because right now it's just looking, who knows what that is. Let's reveal something which might be interesting. So I will just deal with that. Okay, I'm not going to rewrite. I will, no, I need to rewrite. Otherwise, it will be a little bit confusing, right? So summation of Mi Ri double dot. I'm just rewriting this. Delta Ri delta Qj. And very simple procedure. If you take a total time derivative of summation Mi Ri dotted with dri over dqj, and then we need to subtract minus summation Mi Ri dot and dotted with d over dt out of partial derivative of Ri with respect to Qj. Very simple mathematical operation, right? So if you differentiate this with respect to time, you will get R double dot and this left untouched. It's a dead term. But then, of course, you will have to differentiate with respect to this, keeping this untouched, right? So it will be mi, ri, and d over dt out of that. In order to remove that second term, we have this one in order to get that. Very simple, right? Or if you take this to that side, it will be just equal to total time derivative of this. Okay, you see that it's for your level it's obvious. So now, let's use again our ingredients. So this, you see, it's a derivative, Cartesian coordinate, generalized coordinate. The first ingredient, it is equal to the derivative of Cartesian velocity versus generalized velocity. So we can recycle that, start using that. So it's a dvi over dqj dot. Okay, I need to change the green marker. I forgot. All right. So this. And then, of course, I will use blue. This is vi. Then this total time derivative and that partial derivative with respect to qj, we can interchange them. They're independent. So we can basically take this total time derivative and bring it inside next to that ri. So it will give us velocity in Cartesian coordinates, vi. Right? Okay, so, and of course this is also velocity, right? So now I can rewrite this. Summation is there. Probably I will take that sum outside. Yeah. Summation over I, it's not a big deal, because it's confusing me. So summation over I outside, and now let me rewrite using all those substitutions. So it will be mi vi dotted with this dvi over dqj dot. Okay, you know what, that dot will be difficult to see. Let me rewrite it, bring it slightly lower. All right. And my summation is outside mi vi dotted with partial derivative of vi over dqj. Again, as I said, the total time derivative I combined with that r, and it gave me velocity. Conservation of brackets. If you open, number of open brackets must be equal to a number of closed brackets, right? Okay, so now, now we will see the structure is very similar here and here. As a result, we can rewrite it in this form. Summation over, you know what, not summation over I. Now I will bring inside. Let me bring it inside. Yeah. Let me write it this way. D over dqj dot, and okay, let me remove this bracket first. Then summation over I, 1 over 2 mi and vi. Wait, now I don't need this vector, vi squared. Okay, let me check. This first term, I claim that I can rewrite it like this. So if you differentiate this with respect to qj dot, this 2 and this 2 disappears, mi, you will get vi this, and of course then dotted with the derivative of v dvi dqj. Yeah. I claim that the first term can be rewritten like this. Now let's do exactly this. Okay, not exactly, very similar. With the second term, because the structure over here and over there, very similar, except for here we have q dot and here we have q. Okay, so let's differentiate with respect to q instead of q dot in the second term. So minus a partial derivative with respect to qj, and again summation over I of 1 over 2 mi vi squared. If I differentiate, 2 disappears, mvi and yep. Okay, so now we naturally getting the total kinetic energy of the system. Because again, what are those VIs? Just the velocities of each of the particle in the system. All right? So this is total kinetic energy of the system, not of one particle. It's a total kinetic energy of the system. And as a result, we are getting a very nice, oops, okay, let me, a few minutes, right? So we can rewrite it as d over dq. Again, I ran myself into difficult to write. Yeah, I can write it like this. Immediately, partial derivative of t with respect to qj dot minus partial derivative of t with respect to qj. Okay, and again, you remember we just messed with this bracket. Okay, I need to erase this in order to rewrite this. It's still second term. I will put this sign and I will continue it here. Right. So it will be summation over j. And instead of this bracket, I will write what we got over here. So it will be a partial derivative of t with respect to qj dot minus partial derivative of t with respect to qj and delta qj. Let me check. Right. I'm looking that something is fishy, and now this d over dt I lost. Right? You see, I started messing with this rewriting, but d over dt I lost at that point. So next to this term, and you're so quiet, right? Waiting until I embarrass myself. All right. Okay. Because now I'm getting this, and I'm looking, something is missing. Something is not right. So this d over dt. Yes, summation applies to all these, both of these terms. Right. So here I will have to write d over dt. Right. Okay. And here the same. So it will be outside of this term only d over dt. I will put a bracket like this. Right. So, and here the same. So it will be equal to d over dt. Right. Okay, so now also the same here. I have to fix it. Again, if you see that something is not completely right, tell me. So that summation, and in the bracket, I will have d over dt, partial derivative of kinetic energy with respect to qj dot minus partial derivative of kinetic energy with respect to qj, and delta qj equals, oh, not equals. There's no equals. We're just dealing with this second term. So that's what we got from the second term. And now we need to combine. I erased Delambert's principle, but you have in your notes, and that will be the end. All right, I just want to get the rewritten form of the Delambert's principle. So now we need to combine this with that. this term was first in the D'Alembert's principle, minus that and equals 0. But since it equals 0, of course, we can flip terms. We can change order of those terms. I want to write that first, and then this is second. What a big deal, right? All right, so as a result, so D'Alembert's principle will have this form. So now summation over j will be outside. That's what we wanted. Now in the bracket, I will first write that term as I want. D over dt partial derivative with respect to qj dot minus partial derivative of t with respect to qj. And now minus this generalized force with delta q. So minus qj and delta q goes outside, and it must be equal to 0. So this is a new form of D'Alembert's principle written in terms of generalized coordinates. Of course, that t must be written in terms of generalized coordinates and so on. And now, yes, since delta qj's are linearly independent, so now we can say that this can be correct only if all of these factors in front of the virtual, instead of this delta qj's, must be equal 0. So now, since delta qj's are linearly independent, we can write that d over dt partial derivative minus dt over dqj. Okay, let me write with minus q and then qj equals to 0. So basically this, okay, and we call it a day at this point. This we can say sort of like a general form of the Lagrange equation, where we're not imposing any restrictions on forces. Forces can be, of course, they must be actual, right? So, but forces can be conservative or not conservative, we don't care. We haven't imposed any restrictions. So over here, this form of the equation can be applied for a system with friction and so on. So the next step, we will assume what if forces are conservative. Of course, we will rewrite this form of the Lagrange equation, and we will get the typical form of the Lagrange equation. So d over dt partial derivative of L with respect to q dot minus all that stuff. But of course, for that form of the equation can be applied only if all actual forces acting on the system conservative. Here we don't have that restriction. Okay, sorry for holding you, right? So I just wanted to get at least to this point, right? So next class, okay, on Thursday, we will write the actual form of the Lagrange equation. Then, since now everywhere kinetic energy, and of course kinetic energy must be written in terms of generalized coordinates, we will look at all possible terms that we can get out of the kinetic energy if you try to write it in terms of generalized coordinates, because we will need that in the future several times, right? And then we will look at the example, and that will be over about D'Alembert's principle. And we will move to the Hamilton's principle, and again we will get the Lagrange equation, but now from the Hamilton's principle. Right? It's basically the only point next class, or maybe in the class, where there is an overlapping with the graduate and undergraduate level course, because in both courses we derived Lagrange equation from the Hamilton's principle. But it's one of the most important, and I don't feel guilty of having that overlapping. Okay, guys, so if you have questions, go ahead. I don't have classes today, right, after this, and otherwise I will see you next time.